not solving for the roots, but not solving for the poles. Okay, so that will be quicker, very quick method. But the disadvantage is once you solve for this criterion, then you only know the system is stable or not, but you won't know exactly the location of the poles. So basically, the vice versa. Okay, so it depends on the needs, and so. So let me write it up. So let me write it up here. So it is allowed to determine the stability without solving the roots of the characteristic equations. Okay. The criterion is doing this. So we do it symbolically. So we're starting from the characteristic equations. So what is the characteristic equations? And so that means if we have the transfer functions and y as over r of s and equal to polynomial equations, basically that is the PS. Okay, so that's in our notation. So basically you simply take up the denominators polynomial put into 0, so that is PS equal to 0. Okay, so here we define the PS equal to an as n plus an minus 1 as n minus 1. So this is our characteristic equation of the linear systems. So the Routh Hurwitz criteria is based upon the justifications of we call the Routh table. Okay, how to build up this one? So the table is built up based upon the arrangement, and from here onward, just pay attention and just try to do all we can for a few seconds, a few minutes. I'll be done quickly. You won't feel any pain. Okay. So arrange by observing the coefficients of these polynomials and arrange them in such a way. You have to do it precisely, otherwise you would make a mistake. So an starting from here, and then the next one goes to an minus 1, and then for the third one, an minus 2, and an minus 3, until, so basically you do the pattern is like this, okay, until whatever, maybe maybe a1 here, a0, or maybe depends on the terms, okay, you just doing arrange like this. And then from here in to determine, to build up the tables, so that is based upon our given informations. So this row corresponding your highest degree is corresponding is n as n minus as n degree. So this one corresponding is n minus 1 degrees. Okay. So from here, that's going to indicate we're going to fill up the tables, and the table corresponding to the different the degrees, and from here until constant term. Okay, so right now the issue is how can we fill up the number here, and that is go to the formulas, and the formulas is dedicated to the two people, and basically this method developed about in your age, about 70 years ago in the 1950, 1960, about that year. Okay. And so here, let me do it here. So let me call this is, because here I draw it too small, but let me use the table here. So let me say this is B1, okay? And what is B1? I hope you have enough space at the sides. If you like, you can put a B1, B2, and C1, C2. Okay, you can put those symbols. And for better demonstrations, and I like to utilize the advantage of the whiteboard here. Okay, so this is a B1. B1 equal to how much? And do this one carefully. If you have a space, you try to use the space on the sides of your lecture notes. Okay, do this one carefully. B1 is obtained from the given data above, and denominators is an minus 1. Okay, this is the denominators. And then multiplications of the two terms. So an minus 1 times an minus 2 minus the two terms of these. Okay, and probably we should be able to exercise it with one example.